Hello, everyone, and welcome to this seminar hosted by the Princeton AI Club. So our speaker today is Professor Emtiyaz Khan, also known as Emti, from the Riken Center for Advanced Intelligence Project. He is also an external professor at the Okinawa Institute of Science and Technology. Today, he will be talking to us about his recent work on the Bayesian learning rule for adaptive AI. Take it away, Professor.
Thank you, and thank you for inviting me. So I'll talk about some of the work that we did in last few years, and then try to go into what we're really excited about now in the next 5 years or so. So the title is the Bayesian Learning Rule for Adaptive AI, and I thank some of my colleagues, my collaborators who have helped me in making the slides for this presentation. You can find the slides on my webpage, and you can also find some summary of our research. So feel free to have a look at that. Okay, so I'll start with the big picture stuff. So the talk is going to be quite big picture, but if you ask me some questions about the detail, I'm happy to stop and go a little bit more deep. But the big picture of what me and my group has been interested in developing AI systems that learn like humans and animals and other living beings. And when I say that, what I mean is that we want the AI system to be able to quickly adapt to learn new skills and then keep learning it throughout their lives, acquiring new skills like what humans do. And to motivate this, I show this, and I've been showing this for a while now. This is my daughter, and this was maybe 7-8 years ago when she was 6 months old. She was trying to kind of explore the world, and what she does is she's trying to collect some experiences about what is interesting and what is not, and slowly figuring out that maybe the sound that comes from this instrument is the interesting one. So this kind of learning in human is very common, and what we eventually get to after this is after 6 months of learning is that we figure out what we like in the world, what is relevant to us, and what we want to see more and more of. And if the environment around us changes, so this is after 2 months, when ukulele is replaced by a guitar, it's a different environment. She's still able to adapt to this change and able to then produce the same relevant data, the relevant experience that she has seen in the past. So this is what I mean by quick adaptation. And the machine learning methods and the current AI systems based on deep learning, they are kind of like not able to keep this balance between past and new information that they see. So sometimes systems are too slow to adapt, it's too quick to adapt. That's what I want to talk about here in the slide. So they fail because they are too keen on the new information, and they may overfit the data. So this is an example of a bot called Tweet, which was deployed in 2016 in the morning, and then throughout the day, it learned from other people's tweets, and it sort of starts to overfit that data and start to say many mean and bad racist things. So here the system is too quick to adapt, but sometimes AI systems fail because they are too rigid to adapt. So they're too slow to the change. So if you move sort of small things in the environment of a robot, it may not suddenly realize that the environment has changed and that it should be adapting to it. So there's an issue with striking sort of balance between past and new information, and people are extremely good at doing this kind of adaptation, but machines are not. So we're trying to design systems that can somehow be adaptive to new information and robust to the past information that we have seen. So what I want to talk about in this talk is give some principles that should be behind this kind of learning, and I'm going to focus on the Bayesian principle. And what I'm going to argue that the algorithms that we see that we design through maybe intuition and maybe through sometimes hacks and they seem to work very well in practice. My hypothesis is that this kind of good algorithm should have some kind of Bayesian side to them. So there's some inherently Bayesian thing going on. And if you're able to understand that, then maybe we are able to understand how information is kind of balanced between the new and the old information that the system is seeing. So to be able to do that, I'll start with this algorithm that we proposed a few years ago. We call this Bayesian learning rule. Through this, we are able to derive many existing algorithms as optimizing some kind of Bayesian objective in a very Bayesian way. And then using this algorithm, I'll show some initial attempts that we have made to understand the robustness of good algorithm, of how they remember the past. So I'll introduce something called memorable experiences of learning machines. And then once we understand how the past is represented, then I'll talk about how we can adapt it when we see new information in the future. So I'll talk about some kind of encoding of the past knowledge in what we call knowledge adaptation priors, or K priors, and they're built upon memorable experiences, and then they can be used to adapt to the future changes in the system. So the takeaway of the talk is that it's a new perspective of Bayesian principles that are essential for kind of adaptive and robust deep learning. And some of so the work on robustness and adaptation is still not out yet. So, but the Bayesian learning rule is already out. So some of the references I have kind of put here. Most of them are out except the second one. And I hope that the talk will sort of give you a perspective to be able to then read more details in those references. Okay, so let's start with the first question that I said that. Well, we have many algorithms that work well in practice, and we see in deep learning lots of those things that have been derived through empirical efforts. But are there some common principles that explain why those algorithms are good? And that's the question that we started out with many years ago. And the question is of similar nature as this origin of species, where we're saying that there's a common origin. Maybe it's by some natural selection that these species have evolved. And now we're talking about the similar origin of artificial algorithms. We believe that maybe all these algorithms should be optimizing maybe similar objective. And also the way that the optimization proceeds is also had something in common between them. I mean, one thing that is very clear is that somehow these algorithms should strike a balance between past beliefs and the useful new future information. So can we write an algorithm that will optimize a similar objective, and you can kind of change things in the algorithm to derive the good algorithm that we see that work well in practice. Okay, so this paper with my colleague Howard Rue, we have written, and this is kind of the attempt that we made in the paper. It's available on arXiv. And there's a table in the paper that kind of details what can we do with this Bayesian learning rule. So it's an algorithm where we make two choices. We change sort of posterior approximation, and we make some approximation to some kind of gradient that is being used in the algorithm. It's a natural gradient algorithm. And with these two choices, we're able to show that different kind of algorithms in, for example, optimization, in deep learning, and approximate Bayesian inference literature, they can all be obtained by changing these two things. So I've listed the algorithms in this first column, so like gradient descent, Newton's method, and many deep learning algorithms, and then many approximate inference methods that you might have learned in your courses. All of these can now be obtained by making two choices, like changing the approximation to the posterior and changing the approximation to the gradient. So I'll try to now explain this in the next couple of minutes of how the rule is set and what things we can change and how we can derive existing algorithm based on those choices. Okay, so we are saying that algorithms, good algorithms, they probably have a Bayesian origin, so they have a Bayesian side, and so they must be optimizing something Bayesian. So often in deep learning, for example, we think of optimizing just a loss function with respect to a parameter theta, and we obtain like one parameter setting that gives us one model. But we are arguing that we should be optimizing something like this. This is a Bayesian objective, even though you may not see it right away. Even if you're Bayesian, maybe you don't see it. But because the entropy is present here, so if you write this as a variational inference, then this will be kind of, be consumed in KL divergence. And the regularizer term right now is here. So it's not written exactly in the variational inference form, but this objective is essentially the one that you see in variational inference. But here, there's no Bayesian model as such. Rather, there's a loss function, and it could be like an arbitrary loss function. It may not need to correspond to a probability, probabilistic model. So this is a little bit more generalized Bayesian inference. I call this Bayesian principle. So here, what we are doing is that we are not minimizing just the loss, but we are minimizing the expected loss under a distribution, and we're trying to find the distribution. And we're penalizing the entropy of that distribution. So we're saying that the distribution should not collapse to a delta, rather it should spread. And it should spread enough to explain the data, to minimize the loss, but not like too much. So there's a trade-off between how much I spread the distribution and how much I kind of focus on explaining the data in hand. I hope this makes sense a little bit, and we'll go through a little bit more later on to gain understanding of what exactly is going on. But I hope that this is enough. Sorry.
There's no notion of prior here, which people take to be the start of being Bayesian. So I like what you're doing here a lot already.
Yeah.
Yeah.
So yeah, so if you want the prior to be there explicitly, you can put it in the loss and could be there as a regularizer, and then you can pull the log prior with the entropy, and you'll get KL. Okay, so if you look in the paper, that's how it's kind of written, but it doesn't have to be there. It could be maybe implicit regularization, which is there in the algorithm, right? So that's why I think this is a slightly better way to think about things in light of what exists in the modern literature now. Does it make sense?
Yes, perfectly.
Yeah. Okay. Thank you. Yeah. So feel free to ask me questions, because many Bayesians don't realize that I'm actually writing the Bayesian objective, but it's kind of slightly more generalized way, so that we don't, we can compare it to this non-Bayesian thing that's written in the left-hand side. Okay. So then we're saying that all good algorithms should optimize something like what's written in the right. And we say that if you optimize it through this learning rule that we propose, it's called Bayesian learning rule, then we'll be able to show that these algorithms somehow can be derived as optimizing what's written on the right-hand side. Okay. So that's the point here. So Bayesian learning rule, it's a natural gradient descent algorithm. And it's written in terms of the parameter of the distribution. So think of this distribution as a Gaussian distribution maybe, and then it has two parameterization, natural parameterization, I'm calling it by lambda, and expectation parameterization, I'm calling by mu. And if you don't remember what these parameterization really look like for Gaussian, I will show you an example soon, so don't worry about that. So I'm updating natural parameter, and I'm taking the gradient with respect to expectation parameter. And we can gain a little bit more understanding of this algorithm by rewriting, simplifying a little bit more. So for exponential families, most of them, you can actually show that the gradient of the entropy is simply equal to the natural parameter. So you get an update where you have sort of moving average between the old parameter and the new, the gradient. And essentially, one way to interpret this is that you have your old belief, they are incorporated in the natural parameter of the distribution. And the new information is coming through natural gradients. So natural gradients is something called innovation. And this learning rule is trying to now do a balance between the information that comes through the loss function and trying to then add this to the old information that was present in the natural parameter. So this is really the way to think about it, is what we argue. And in the paper, then we show again and again that this rule is kind of repeated to derive many algorithms, and it's quite insightful, is what I would say. It's not something that it's not just something very narrow. It works quite widely, and I really am struck by its beauty, that somehow by using this information geometry, so like using natural gradients, we are writing these gradients. These are not gradients with respect to lambda, but gradients with respect to mu. So there's something like Fisher that's multiplied in the front of the gradient. And using this information geometry, we are able to sort of balance the new and the old information. And this is the hypothesis that I'm putting forward now. And the claim is that now if I take this learning rule, and now I can make two choices. So I can change the form of the distribution, so Q. So I could choose different posterior approximations. And I can then make certain, to estimate this gradient, to compute it tractably, I'm going to make certain approximations. And these two approximations together will give me a variety of learning algorithms. Okay, so let's just get started with the simplest kind that we know, gradient descent. And so gradient descent is like this. Just update the parameter using the gradient. And I claim that if you choose the Q to be Gaussian with a fixed covariance, it's a very, very simple example, and it's not a surprise at all. Actually, if you do the calculations just a little bit, you realize that this is true. But then we'll see that the same process sort of repeats the whole time. So we write down the distribution. So I have chosen the covariance to be identity here, but it could be anything really. And then in this case, the natural parameter and the expectation parameter, they're both the mean. And the entropy of a Gaussian with a fixed covariance is a constant. Okay, so I can then take the Bayesian learning rule. I could just plug these quantities inside. And essentially, I just plug this in. So lambda is just m, mean, and mu is also m. So it just comes out to be something very, very simple. And then now the only difference between these two is that I'm taking the expectation here, and I'm not taking the expectation in the gradient descent. So because there's no distribution in the non-Bayesian method, you don't see that directly. So essentially, one can see the gradient descent as a very crude approximation of this Bayesian algorithm, where the expectation is ignored, and it's approximated only at a point. So it's at the mean. It's the most greedy place where I can evaluate this expectation. So in statistics, this is called delta method. And if you just simply approximate the expectation at the mean, then you see that you recover gradient descent. And gradient descent then can be seen as estimating the parameter, the mean of the Gaussian. Many times people don't like this approximation. I understand why there's a hesitation there, but essentially what I'm saying here that the gradient descent algorithm is a simplistic version, can be seen as a simplistic version. So there's no mini batching here. There's no noise. So everything is full batch. So there's no noise in the system. And in that case, it's resembling to a kind of ignoring the noise that could have actually been injected. And stochastic gradient descent is more like what I'm showing here. And there have been actually papers by a couple of people who have shown how SGD is also doing some kind of approximate Bayesian. So we'll get to that in a minute. But before that, let me just say the main point, what I've been actually trying to do for 2-3 years I spent on this part is that now that I know that gradient descent is a simpler version where I ignore the expectation, I'm trying to now understand what happens if I put the expectation back in. So I'm going to remove this delta method, and I'm going to design some new variants of these deep learning algorithms that will then help me to estimate uncertainty. So the main point here is not to kind of focus on the delta method, but to see it as like, if the expectation is not there, I could be a bit more Bayesian by adding the expectation in the learning rule. And that will then give us slightly better, hopefully slightly better methods. So if you're convinced by that, then maybe let's look at a little bit more what the expectation is doing in this objective. Okay, so for this, what I'm going to show is that suppose that you have a loss function like this, and it's clearly non-convex, have multiple minimums, and maybe this is the most dominant one. If you were to choose your approximate posterior to be a Gaussian, then you can look into the expectation of the loss with respect to the mean and the variance. Right? So if I try to increase the variance, you see what happens here. So essentially what's going on here is that as I increase the standard deviation, you see that it's sort of some of the local minima, they're disappearing. And the more dominant one is remaining first. It stays for as the variance is increased. So the expectation is kind of a Gaussian convolution, and or maybe you can think of it as like adding noise of Gaussian type in your parameter. And that perturbation essentially has the effect of making some of the minimas go away. So it's making your objective function a little bit smoother, maybe a little bit flatter in certain direction. So you can expect that when you optimize this objective, you'll get to more stable solution. Now, this is really an idea that is really inherently Bayesian. It's been there for many, many years from very, very old times. Recently, people have been kind of talking about this idea that we should optimize not the original loss, but something different than the training loss that you have, because you don't want to really overfit to the training data. And in deep learning, this is now being called implicit regularization, that somehow the noise in SGD is being injected there, and because of that, the algorithm doesn't really optimize the training data, and it avoids overfitting and finds more stable solutions. So this is really related to that. And what you can actually argue by looking a little bit more into the solution. So here I show for gradient descent, you find the solution theta star. That's just one model parameter setting. And you set the gradient to equal to 0. But if you look into the minimum of the Bayesian learning rule, you'll find that it's actually not trying to find a stable solution where the gradient is 0. Rather, it's going somewhere away where the gradient of the expectation is 0. If you stare a little bit more into it, eventually you realize that you're trying to inject noise through the distribution, so Q distribution, so some kind of Gaussian noise is being injected, and you're taking the derivative with respect to that noise. And then it has a similar regularization effect to the noise in stochastic gradient descent, that it prefers flatter direction. And the version that's actually written in the paper, it's in equation 25, and I will encourage you to check that out. But essentially, what happens there is that you can imagine a situation where you are in a place, so your minimum is at a place which is kind of unstable place. So you can think of it as like, if you move slightly in that direction, you'll hit a wall suddenly. So suddenly you will have very bad model. But if you move slightly in that direction, in the opposite direction, I hope you can see my cursor, but if you move in that direction, then in the other direction, then it's kind of flatter. So less is happening, so it's less dangerous. So what a stable method would do is that it'll try to avoid this really huge cliff, in front of you, because you don't want to be, you can invert the situation and think of it as like, you're standing right next to the cliff and you feel afraid that you will fall and die. So you try to go away from the cliff to a more stable position. If you use the expectation, that's what it does, really. And this is explained in Bishop's book. It's called zero avoiding property, for example, that it's somehow this large loss is spilling when you take the expectation. And because the distribution is symmetric, it has to move the mean to the other side. So this kind of noise that is being injected, it somehow pushes you to the more flatter direction. And if you actually run SGD on this problem, you will see really exactly this phenomenon. And I don't have time to show it, but if somebody wants to see it and ask me a question, I could probably pull that slide up and show it to you. So in the sense of time, I will skip that one, but you could see why the solution would be moving towards the flatter solution if you did an expectation or if you injected noise through SGD. They both have very similar effect. Okay, let me move on to the other big point of Bayesian learning rule that is really incredible, that there is a one-to-one relationship between the complexity of posterior versus the complexity of the learning algorithm. So let me properly define what I mean by complexity. So just imagine that there is a posterior distribution of the problem. So you could think of it as like a Gibbs measure. So e to the power minus of loss. It's called Gibbs distribution sometimes. So this might be the mode, and then your neighborhood is shaped like that. And if I choose a very, very simple posterior approximation, like what I did for gradient descent, is just a fixed circle where the variance is not changing. It's constant. And if I just want to estimate the mean, I showed you that I get gradient descent out of Bayesian learning rule. So now I can increase the complexity of the sufficient statistics. So I can not only just estimate the mean, but I can estimate the covariance as well. So that's going to 2 degrees of freedom. And in that case, my circle, now I'm allowed to change the shape of it. So I can capture more of the geometry of the landscape. And if I do that, then if I plug this thing in the Bayesian learning rule, I get a Newton's method out of it. So it's the same equation that essentially spits out a more complicated algorithm out of it. If I then go to more complex posterior, so if I do mixture of Gaussian, you can actually guess it. You have to estimate the mean of the covariance of each component. And so you have multiple mixture of Newton method. It's like an ensemble method that you're running. It's like doing multimodal optimization, going towards different places in the landscape and try to cover as much as possible. So you see that the complexity sort of increases, and you can show that in cases where you're able to compute the exact posterior, and if you plug that in the Bayesian learning rule, then you will recover what Bayes rule would give you. So it really holds true that as I increase the complexity of the posterior approximation, I get more complex learning algorithms. Okay. So this is explained in the paper, and everything else kind of very mechanical that I will, I write down the natural parameter, expectation parameter in this case, and I plug it in here. I do like all of these simplifications and just kind of let it kind of, so there's some magic rules that come in here to write down these natural gradients. And if you, so there's no approximation so far, but if you just write these things, then you end up with an algorithm where you have gradient and the Hessian. And I'm not going to go through the detail here, but you can see it in this paper and also in the Bayesian learning rule paper. But essentially, this algorithm, if you kind of say that the step size is more like Newton-like, it's like very quadratic shape, then this Bayesian learning rule, this will become very much like Newton's method. But if you want to be more Bayesian, then you should maybe be here, and we should also maybe put the expectation back in and then sample from your distribution. So that's what we have been sort of saying. What we figured out, what we realized actually is that if you look at this algorithm, So just pay attention to the moving average here, that 1 minus rho and rho of the Hessian. Then it looks very much like what we have in deep learning algorithms. So we took this this idea and we tried to kind of see what differences we have between these algorithms and RMSprop. That's the simplest one that we could think of. So here you see that in RMSprop, you do this kind of moving average of the scale S, and you're taking the square of the gradient. While in the Bayesian learning rule, the thing that I showed here, you're computing the Hessian. So it's the same moving average, but you're computing the Hessian. But you're using the scale S. So this is actually inverse of the covariance matrix in this case. But you are using the covariance matrix, which is the inverse of the S matrix, to scale the gradient, which is exactly, not exactly, but which is very similar to what's happening in RMSprop. So we try to then bring down Bayesian learning rule to be in a very similar setup as RMSprop, and we call this variational online Gauss-Newton, because to implement it in an easy way in the existing deep learning framework, we didn't want to compute Hessian. We computed something like square of the gradient. And we show that if you did this, then this S, because it's related to the inverse of the variance, you can essentially just compute the variance for free from this RMSprop-like algorithm. So this, we have done like three, four versions of this algorithm. We've been improving it over time. And when this was presented the first time, well, it was published the first time. At the time, this was kind of the first algorithm that was able to get good performance, similar performance to Adam at ImageNet scale. So this is the first Bayesian algorithm. I'm sorry if I didn't say that clearly. So we call this variational online Gauss-Newton VOGN method. It's the modification of Adam. So we added momentum to it, and that also comes very naturally in Bayesian learning rule. And what essentially happens here is that instead of estimating just one line, so this is one blue line, now we estimate the mean, which is the red line, and then some samples from it due to the variance that's not very small. So you see that you get multiple solutions that explains the data well, and this is very Bayesian in nature. And then we apply this to ImageNet data set, and there we're able to get very similar performance to what SGD and Adam are actually doing. So we're able to get the same accuracy, and we get uncertainty estimates that are better than what you get with Adam. And then last year, some of the group members, they took the most modern version of this, which is in this Lin et al. Paper. It was published in ICML 2020. They took that variant and they applied it to Approximate Inference challenge, where really they didn't have to work very hard. It just kind of worked out of the box. So the new version is even better and easier to tune and to run. And they're now writing a paper on this to explain how this kind of Bayesian learning rule inspired algorithm can be used with mixture of Gaussian posteriors on like a variety of deep learning benchmarks. Okay, so I've kind of finished the first part. And I think I have 37. Okay, so if you have any questions, I'm happy to stop here.
I have a brief question, Emti, if I could.
Yeah.
So I was wondering about the complexity of the solution. Like, what does this do to the sort of number of flops that are required, or some other metric where we can evaluate how a Bayesian learning rule version compares to other things like Adam? What's the sort of way of thinking about this?
Yeah, that's a great question. Yeah, so I think the idea is kind of like as you throw more, you increase the complexity of the algorithm in terms of like you're trying to estimate the posterior better, right? So you're going towards more complex aspect of the posterior, then you will see that the compute will increase. And the hope is that as you add more compute, you get better estimate of uncertainty. And in this algorithm, you can, I hope I'm answering your question, right? But in this algorithm, this kind of comes in like number of samples that you inject. So if you just use one sample, then the complexity is exactly the same. And as you increase the number of samples, then you will see that the estimate of the uncertainty gets better. Then another thing that you can add is that you can run multiple chains of this. So you can add, let's say, 2 chains of this VOGN-like algorithm. Then you're going to try to estimate a little bit more about the neighborhood. So you'll have like 2 models, like 2 posterior, 2 Gaussians, from which you can create many models by sampling from them. So you could sort of see one-to-one correspondence in, as you increase the number of samples, number of components, the complexity of the posterior that you're estimating, the algorithm becomes more complex, then it takes more.
Right, I see. Thank you. Yeah, that's helpful. And if we're learning this posterior as well, then I guess that information is not being thrown away either. We're not losing that.
Exactly.
Yeah,
Exactly.
that's great.
Yeah, I mean, a few years ago, we were stuck at this square of the gradient that we got a lot of criticism from people about that, but this is not a hurdle anymore. So there's no other difference. Like in the newest version, it's like very similar to this. Like we don't need this kind of bottleneck. So the complexity is now directly tied to number of samples or number of components that you draw, which is very nice.
Great, thank you.
Thanks. So yeah, I mean, I didn't explain this, but maybe I'll continue. There's also like, again, this flatter minima argument again shows up if you start to estimate the covariance. Now you're going to go to regions where you try to like, increase your variance and you settle into this one compared to this one if you're also adapting the covariance. So naturally, there's always stability that's kind of built in. That's just a demo on some real problems done. You could probably get better results than this. But if you like all of these things, just, this is really old material that was done until 2019. Since for last 3 years or so, now we are kind of taking all of the stuff that was done before and now looking into this adaptation and robustness, the trade-off between that. But if you're interested in that stuff, then please have a look at the Neurips tutorial that I gave in 2019. Okay, sorry. Okay, no. Okay, so let's now get into, so I have about, maybe I can go 10 more minutes. I think I'm going to go 15, but I'll try to finish in 10. And talk about robustness and adaptation. And I'll be very fast in this, and I apologize if the details are not really there. Talking about robustness, a good algorithm, as I said, it should be able to somehow tell apart what is relevant and what is irrelevant, right? Like my daughter, when she has learned, she's not like, touching everywhere. She's only kind of going to the relevant fretboard where the sound comes from, the music that she likes. So there should be this kind of robustness to past learning in systems, in good algorithms. And so how can we kind of understand this and then use this to adapt this knowledge? And I've spent a lot of time in this, and I've realized that I don't like to write quick papers in every conference. I've taken a long time, maybe too long. But I think it's worth it, and I'm enjoying it a lot. And what I've realized is that the fundamental concept behind this idea of to understand what part of the system is robust, where the knowledge is stored, is to understand it by perturbation, then sensitivity to this perturbation. And this concept is actually very classical, old concept that's realized through duality. So it's some alternate representation. It's a dual space where the sensitivities are represented, and they're equivalent representation to what we see in the model parameter, for example. I've been trying to formalize this for a few years, and it's it's complete now. So just writing and finishing this paper, which it takes time. It's a long paper to write, but the sketch is kind of quite simple. So that suppose there is a system. So this is a system. It's made of certain parts, and in deep learning, it's kind of data. So many data examples, the n data example, and maybe 0 is the regularizer. Okay, so 1 to n is the data example, and the 0 to 1 is some kind of small regularizer, implicit, explicit, something like that. And if you apply the Bayesian learning rule to it, you see that the new information now is like new information of each loss function. Right? So it's very, very intuitive. That's what you would get. Now, what actually you see that this system, so I'm going to just show it the solution of the system. So there's the duality here naturally, and I'll just show this for the solution, although it holds for the updates as well. So at the solution, what will happen is that this lambda will be equal to this gradient. So that's the fixed point of this Bayesian algorithm. And this lambda is the global, I'm going to call it global natural parameter. So it's the natural parameter of the distribution Q. And it consists of what happens locally at every data point. Okay, so at every data points, you get new information, and it's the natural gradient of the loss. Let me call it some kind of local natural parameter. So you could see the global one is the sum of lots of small local natural parameters. So you can already see that if you want to understand what is relevant information right now to this distribution that's being learned here, is that so I've indicated this by lambda tilde I star. The lambda tilde, if it's very big for certain data examples, then they contribute more to the sum. So this is kind of addition. I call this conjugate computation actually a long time ago. But when you're adding these natural parameters, the ones that are really big contribute the most. So you could say that if you want to figure out what is relevant, you look into the natural parameter that is the largest. The story doesn't stop there, and that's why it's taken me a long time to formalize this. It turns out that actually I can write an equivalent objective function where I can show that these small little lambda tildes, they're actually Lagrange multipliers. So they're somehow capturing the sensitivity of the solution lambda star. So you can think of it as Q distribution that you learn. And if you remove like a loss function from that, from this, one individual example, and you look at the resulting loss function, you retrain the system, how much the new system will differ from the old one is captured, that sensitivity is captured in this lambda tilde. Okay, so this is really remarkable, and I didn't think that this will be true, but it is, and it's a very pleasant surprise to see. So now I'm kind of trying to formalize this. So I formalize this, and I'm trying to show why this is actually an important concept that we should all pay attention to. So one thing that has come out of it, and this paper is not out yet, so it's called Memorable Experiences, where if you start to look into these lambda tilde i's, then you start to understand, like in an MNIST, if you take a trained network and you look at the lambda tildes that are very small, they correspond to examples that are very regular. They're kind of easy to predict, easy to classify. But the ones for which lambda star is big, it happens in kind of two ways. And some of them are kind of outliers. So it's a 3, but it's actually mislabeled. So it's 5 and 9. 4 is 7 and 9 actually. So for these examples, the lambda tilde is big. And then there are other kind of examples for which lambda tilde is big. These are uncertain examples that are kind of difficult to predict. Maybe they're very close to the decision boundary, so their uncertainty is quite high. So we're able to kind of figure these things out, and I'm going to skip that other one. And then the amazing thing is, again, the same story, that if you change the posterior approximation, you make it a little bit more complex. You see that more, criteria to categorize the example will naturally emerge. So like here, okay, I'm not going to go too much into detail, it turns out that you can sort of change the distribution, change the loss function, and you can get like support vectors out of it. You can get classical influence function out of it. Some other things that in GP literature, people use inducing inputs. You could show how they are related to this kind of construction that comes out of lambda tilde. Okay, and then no other computation is needed here, really. Like, you just look at the solution, you try to find these lambda tildes from the solution, and you're able to then use that to get the sensitivity of the posterior that you're able to understand through lambda tilde. So this concept we've been working on for a few years now, and we call this Bayes-Duality because it's a notion of duality that generalizes a lot of existing notions, like those in information geometry, in optimization, and many other fields that have, like Bayesian non-parametrics, for example, and Gaussian process. And we've been very fortunate to receive quite good and generous funding from the government on this with a couple of amazing people. And if you're really interested in collaborating with us on this project, please feel free to reach out to us. Okay, so I took a little bit more time. Maybe I'll do the adaptation part very quickly, go to the question, and then if you have a question, I can actually explain more details. So the last bit of the puzzle is about adaptation. Like, now I understand, some lambda tildes, these Lagrange multipliers, they're larger and the system is more sensitive to them. Now, how can it help me to add new knowledge, adapt to new information that's coming in the future? And the sketch is actually quite simple, is that if I understand what is important in the past, so for example, if I'm given this 2 classes and I understand that these examples are memorable, meaning that lambda tilde is high for them in some sense, then I can freeze this knowledge, and I say I don't want to lose this. And when I see the new class, I try to classify this new example by kind of not interfering with the old knowledge. So it's quite mechanical in the sense that you just freeze it. This is one way to do it. It's maybe not the best way, but you can kind of do continual learning in this way to avoid the past. And we try to apply this to some real, some benchmarks that people have been using. So usually in the Bayesian framework, people use a weight regularizer, which looks like this, and it's called EWC methods. It comes from this Overcoming Catastrophic Forgetting paper. And what we actually show that if you use the dual representation, which is actually in this case is just a GP for the Gaussian posterior, it turns out to be just a GP, and that's written in this paper. Okay, so this is wrong. This 2 should be 3. So this is the 3rd reference. And essentially, you just replace this weight regularizer by a functional regularizer. And if you look at it, it kind of does the right thing. So we don't have time to go over it, so I'll skip this. But we've been then showing that, again, what really happens here is that you go to the dual space, you look into this dual parameterization. It turns out that when you write these Bayesian regularizers, then they're actually trying to approximate the past gradient. So they're somehow injecting noise such that the past gradients are reconstructed in a faithful way. So these samples from the posterior can be seen as something that is trying to keep you close to your past. So to me, actually, there's no question now, and I'm trying to communicate this to you and many other people in our community, that there's a strong evidence that all of these things will have Bayesian rule. If you want to design an adaptive system, you will have something, Bayesian principles, Bayesian side to them. And maybe you don't come to it by really, starting from Bayes rule, and maybe you did some kind of other approximation, something, but by understanding this Bayesian side to it, perhaps it helps us to maybe unify these hacks and bring some principle back to it. So that is really what I wanted to say, and yeah, I will end with that. This is the group. The group has been growing, fortunately, and many amazing people. And we're very happy if some of you would like to come visit us or collaborate with us and want to know more about our work. So thank you for listening.
All right, thank you for the very interesting presentation. I guess we have some time for questions from the audience. So actually, I do have a question regarding this notion of memorable experiences. Like if you go to that slide where you showed the examples using MNIST, it seems like basically the examples for which lambda is large and which are memorable are those that are actually, I guess from an intuitive human perspective, those that are actually a bit more unclear or ambiguous, rather than those that are, I guess, easy, which are things like to be more clear-cut and well-defined. So is it kind of just true that basically these memorable experiences correspond to just basically examples that kind of lie at the edge between classification boundaries, so to speak?
Yeah, I wish that was true, right? But so this is kind of why the paper doesn't come out so quickly, because it has to be written with care, not to give an impression that it's only the difficult things that matter. I mean, the truth is that it's a mix of experiences that makes us, as an individual, who we are. So what we actually see is that we need to look into the dominant direction of these lambda tildes. So look into the space, see the orthogonal axis that describes that space. And then those are the ones that we should have a healthy mix of this. Actually, people in online learning community have been doing this for ages, by the way. So they have these kind of things that call leverage score and sampling in like linear model and also DPP sampling. There's a lot of good ideas there where people have thought about exploitation trade-offs. So the easy example versus the difficult example, it comes because of you need a trade-off. And that's why you don't have like one answer to all the solutions. And I feel very sad to see a lot of deep learning papers going only after difficult example, or going only after like uncertain examples, or there's a lot more here to understand and do it properly. But thank you for your question. Maybe I answered more than what you needed to know. But
so actually, just to maybe as a small follow-up, so it's kind of like to understand basically the easy examples are kind of define the direction for which the orthogonal direction for which you mentioned in conjunction with the difficult examples which are near the boundary.
Exactly, yeah. So you want to get those orthogonal directions, and then when the new data comes in, if it adds a new orthogonal direction, then that's worth paying attention to. And if it doesn't, then it is already been learned. Right, so that is what is the difficulty of adaptation.
Yeah, thank you. That's very clear.
Could I jump in with a related question? I find this dual space representation really exciting and yeah, really elegant mathematically. So thanks for sharing that. And I'm wondering, I want to bring up the classic objection to certain Bayesian methods, which is, how do we know our model is sufficiently specified that these sort of sensitivities of the posterior are giving us information that is, good or correct to know what we should memorize at a certain point. Maybe maybe we didn't know what MNIST was, and we chose too few classes, or we chose a mixture of Gaussians, which didn't have sufficient complexity or something. I'm just curious sort of how you're thinking about this. Like a Bayes factor question. It's like, how we can compare within the models, but how do we know outside of that? Does this give us any hooks into that difficult problem?
Yeah. I've thought a lot about this. So this is a great question. And I think many times people are too quick to reject Bayesian methods because they say, oh, model misspecification. But any method is. So you have your loss function and you write it and you add some data examples, and it always has this issue that it knows certain things, and then certain things it can't possibly model, but then other things it is beyond it. Right, so because that's how this construction works. Again, the principle is you cannot have more than this. you know something in the past, maybe you don't know anything, and you call that prior distribution. And then you see something, and you see how to balance those two. So the Bayes rule is the most natural way to write it, but it will not do exactly the right things if your model is not right, and neither will any other method, right? So you need extra support there. Whether you're Bayesian or not Bayesian, this question doesn't change. The principle goes in the same way. You know something, you represent that, new thing comes in, you check how it fits with it. But if your measuring instrument is wrong, then you get wrong answer. And then life tells you that, in the future. So I don't see it as a debate. I just see it as a kind of people feel that maybe Bayesian methods have this problem and other methods don't have that, which is not true. And other methods can do this in a better way. Well, the principles are kind of the same. So the difficulty that you face, they're of very similar nature. Like you could do conformal methods or other things, but
yeah, I totally agree. And I think maybe even this posterior sensitivity could be a way of diagnosing when the model is sufficiently misspecified. If you can do some exploratory data analysis and pair it with posterior sensitivity analysis like this, you can see, hey, this data point, which should have, been quite relevant to my classification decision. Now I can see quantitatively that my measuring instrument, my sort of choice of complexity in the posterior was inadequate. So it seems like a really great sort of addition to this discussion.
Yeah, I mean, the way that we should think about it is that if we had only point estimate, we were better off. If we had a little bit more information, like samples about the neighborhood, we really have more information. It's about how we use it is kind of, is what we should be thinking about rather than whether we should be Bayesian or non-Bayesian. So thanks for asking that question. Like, cold posterior talk. I very strongly disagree with how that was presented, and I think there's more to the story than what we are actually making it to be.
Great, thanks for your answer.
All right, I think we have a question in the chat from Tim asking whether the cold posterior effect would affect variance derived from the Bayesian learning rule.
The temperature, let me say, will, yes, of course. So I think the rule is not complete, right? So it's about the objective, and so objective. When you write this objective down, you may need to kind of understand how should you, as the new data arrive, how should I balance the entropy versus the loss, right? So if the loss is not defined in the right way, maybe it's every time it's fooling you slightly, and then maybe you need to kind of adjust it, weigh it appropriately, so that the entropy, the posterior variance doesn't shrink. So you need some kind of scheduling. You need additional help, and for that you will have to implement something extra. So this rule will not help you. So yeah, so you're right that the variance will be affected indeed. But it can be fixed. It's not like the world is better if you're in the minimum of L, in the left-hand side than the right-hand side. What I'm saying is that in the right-hand side, you're much better positioned to handle it than in the left-hand side. So we shouldn't forget that. So Bayesian deep learning is like, it fooled me is not the right narrative. I would say you fool yourself, is what I was. I'm sorry, Sebastian, if I said that too loud. If you ever watch this.
Okay, so I guess if there's no further questions, let's all give another round of applause to our speaker. Thank you for the very interesting and insightful talk. And yeah, thanks everyone for coming to the seminar.
Thank you for inviting me. Thank you.
Yeah, thanks. All right, I think I will stop recording here.